Today's topic is Maxwell-Boltzmann statistics. There are two types of statistics. One is classical statistics. Maxwell-Boltzmann statistics is example of classical statistics. Other statistics is quantum statistics. Bose-Einstein statistics and Fermi-Dirac statistics are quantum statistics. So, first of all, we discuss Maxwell-Boltzmann statistics, which is classical statistics. To study many particle system, Maxwell and Boltzmann postulated classical statistics using laws of statistical mechanics. This statistics is known as Maxwell-Boltzmann statistics. Basic assumptions of Maxwell-Boltzmann statistics are following. These are the basic assumptions of Maxwell-Boltzmann statistics. Number one, this statistics is applicable to those systems in which particles are identical and distinguishable, and their spin may assume any value. So, first assumption is this, that this statistics, Maxwell-Boltzmann statistics, is applicable to those systems in which particles are identical and distinguishable. Distinguishable means that we can distinguish any two particles and their spin may assume any value. Number two, since particles are distinguishable, by exchanging two particles, we get new microstates. Number three, minimum volume of phase cell in phase space is H0 cube. In phase space, we consider a small volume element which is called phase cell, and this phase cell represent a microstate. In Maxwell-Boltzmann statistics, minimum volume of this phase cell in phase space is H0 cube, which we can assume as small as we want. H0 here is arbitrary constant. We can choose it as small as we want. And number four, there is no restriction on number of particles in a phase cell. In a phase cell, it can contain any number of particles, 0, 1, 2, 3, 4, 100, 500, 1000. So these are four basic assumptions of Maxwell-Boltzmann statistics. Now we will find the distribution law for Maxwell-Boltzmann statistics. To find a distribution law, consider a system of n, capital N, identical and distinguishable particles, among which no mutual force is acting. So we consider a system of capital N, total number of particles is capital N, and these particles are identical and distinguishable. We can distinguish these particles, and we also consider that there is no force is acting between these particles. For example, we can consider ideal gas enclosed in a vessel. In ideal gas, intermolecular attraction force is assumed as 0. No force is acting between the molecules of ideal gas. We distribute these particles in phase cells, that is energy states. So total number of particles are capital N, and we have to distribute these capital N particles in different phase cells, that is energy states, in such a way that in first cell number of particles are N1 and their energy is E1. So capital N particles are distributed among various cells. N1 particles have energy E1, N2 particles have energy E2, and so on. So we distribute these particles in such a way that N1 particles are in first cell having energy E1, and in second cell number of particles are N2 and their energy is E2, and similarly for other cells. In general, number of particles in ith cell are Ni and their energy is Ei. There is no restriction of number of particles in a phase cell. In a phase cell, there may be number of particles may assume any value. From this distribution, we want to find most probable distribution, thermodynamic probability of this macro state, that is number of micro states corresponding to this macro state. W is equal to factorial n upon factorial n1 into factorial n2 into factorial n3 and so on. So total number of particles is capital N. Out of these capital N particles, N1 particles are in first cell having energy E1, N2 particles are in second cell having energy E2, N3 particles are in third cell having energy E3. Then for this distribution, for this macro state, number of microstates are given by this formula, and this number of microstates is known as thermodynamic probability, and we write it by capital W. So W, thermodynamic probability of a macrostate, of this type of macrostate, is given by this formula. So these are different cells. N1 particles are in first cell having energy E1, N2 particles are in second cell having energy E2, and so on. Ni particles are in ith cell having energy Ei. So For this macrostate, thermodynamic probability W is given by this formula, W equal to factorial n upon factorial n1 into factorial n2 into factorial n3 and so on. In denominator we have factorial n1, it is the factorial of number of particles in first cell. Then we have factorial n2, it is factorial of number of particles in second cell. Then we have factorial n3, it is the factorial of number of particles in third cell and so on. And in numerator we have factorial of these total number of particles n1 plus n2 plus n3 plus n4 and so on, and it is equal to capital N. So in numerator we have factorial of capital N, the sum of n1, n2, n3 and so on. Now if each cell or energy state is divided into energy levels such that there are Gi energy levels in ith energy state of energy Ei, that is degeneracy is Gi. Now we consider that these n1 particles which are in energy state of energy E1, these energy states of energy E1 are divided into G1 levels. G1 is the number of levels having same energy E1. Similarly, the cell of energy E2, energy state of energy E2 is divided into G2 levels, and in a similar manner if we consider energy state of energy Ei, these are divided into Gi levels. These Gi levels are of same energy Ei, and Ni particles are distributed among these Gi levels, each having same energy Ei. So this Gi, which is the number of levels of same energy Ei, is known as degeneracy for energy Ei. Degeneracy means number of energy levels having same energy. So if the distribution is like this, n1 particles are distributed in energy state of energy E1, and this energy state is divided into G1 levels, then these n1 particles are to be distributed among these G1 levels, and in a similar manner these Ni particles are to be distributed among these Gi levels of same energy Ei. Now in this case the thermodynamic probability will become W equal to factorial n upon factorial n1 into factorial n2 into factorial n3 and so on. This is like previous equation when there is no degeneracy, and if we now consider the degeneracy, then we have these terms also, G1 to the power n1 into G2 to the power n2 into G3 to the power n3 and so on. If n1 particles are distributed among G1 energy levels, then thermodynamic probability will become G1 to the power n1. Similarly, n2 particles are to be distributed among G2 levels, so we have to multiply by G2 to the power n2 and so on. So for this type of distribution, thermodynamic probability W is given by this relation, and this relation we can write as W equal to factorial n. Then we have multiplication of several terms. We have multiplication of these several terms like g1 to the power n1 into g2 to the power n2 into g3 to the power n3, and the multiplication of these several terms can be written as pi I gi to the power ni. Here the symbol pi I represents the multiplication of different terms. Pi I gi to the power ni means that we have to put the value of I equal to 1, 2, 3, 4 and so on, and we find different terms. If we put I equal to 1, we find g1 to the power n1. If we put I equal to 2, then we find g2 to the power n2 and so on. And we have the multiplication of all these terms like this: g1 to the power n1 into g2 to the power n2 into g3 to the power n3 and so on. So this multiplication of several terms can be written as pi I gi to the power ni. Similarly, in denominator we have multiplication of these several terms factorial n1 into factorial n2 into factorial n3 and so on. This can be written as pi I factorial ni in denominator. So we have pi I gi to the power ni upon factorial ni. Pi I it represents the multiplication of several terms for I equal to 1, 2, 3, 4 and so on. So this is the relation for W, that is thermodynamic probability, and we write it as equation 1. Now we have two more equations. One for capital N, total number of particles, and other is for capital E, total energy of all the particles. Total number of particles, capital N, will be equal to N1 plus N2 plus N3 and so on, and it is written as summation Ni. Similarly, since N1 particles have energy E1, each having energy E1, then energy of N1 particles is N1 E1. N2 particles each have energy E2, then energy of these N2 particles is N2 E2 and so on. So total energy of all the particles will be equal to N1 E1 plus N2 E2 plus N3 E3 and so on, and it is written as summation Ni Ei. Correct this, it is not inside the summation we have Ni Ei, it is not Nie. Capital E is equal to summation Ni Ei. It is N1 E1 plus N2 E2 plus N3 E3 and so on. So we have these two equations, equation 2 and equation 3. Total number of particles capital N equal to summation Ni, and total energy E is summation Ni Ei. By taking log of equation 1, this is equation 1 for W, for thermodynamic probability W. If we take log of this equation, then we find log W, and log W here is written as ln W. ln W means it is log W for E base. So log W now will be equal to log factorial n, W equal to factorial n into pi I gi to the power ni upon factorial ni, So log w will be equal to log factorial n, it is first term. Then we write plus, and then this pi I is changed to summation I. Since the log of multiplication of several terms like log a into b into c is equal to log a plus log b plus log c. So if we take log, then the multiplication will be changed to plus sign. So this symbol pi I will now change to summation I. Summation means it is the sum of several terms. It is the addition. And then log of gi to the power ni is ni log gi. And then in denominator we have factorial ni. Then its log is given by minus log factorial ni. So log w will be equal to log factorial n plus summation I ni log gi minus log factorial ni. For large values of capital N and ni, using Stirling's formula, this is Stirling formula, log factorial n equal to n log n minus n. Similarly, log factorial ni will be equal to ni log ni minus ni. Correct this in equation 6. In left hand side it is log factorial ni. Log factorial ni is ni log ni minus ni. So we substitute these values of log factorial n and log factorial ni in this relation, and we find log w equal to n log n minus n. It is for log factorial n using Stirling's formula. Then we have plus summation I ni log gi minus, then for log factorial ni we put ni log ni minus ni. So it becomes minus then it is not log factorial ni, it is ni log ni plus ni. So correct here in this term we will have to put the value of log factorial ni, then it will becomes equal to ni log ni minus ni. Then here we get minus ni log ni and plus ni. In next equation we also write, we have to correct this, it is not minus log factorial ni, it is minus ni log ni. And this summation I is for all these three terms. So for last term it becomes summation ni, and summation ni is capital N, total number of particles. So last term is plus capital N, it is summation ni. Summation is for all these three terms. And the previous term is not minus log factorial ni, it is minus ni log ni. So in the summation I we have two terms, ni log gi and then minus ni log ni. So correct this, it is ni log gi minus ni log ni. This capital N is cancelled. Here we have plus n and here we have minus n. So this is cancelled out, and the remaining terms are log w equal to n log n plus summation ni log gi minus ni log ni.